Welcome to qnawire.
So for this question, E3 ends up being 20.66 electron volts for the neon, and E2 is 18.7 electron volts from the figure. Energy here, E, is equal to Planck's constant times the frequency, which is equal to hc over lambda. And this is how we're going to find the frequency and the wavelength of this light emitted from this transition. So E, which is equal to hf, is equal to, since energy is conserved, this is going to be equal to E3 minus 2. Notice F equal to E3 minus E2 over lambda, or excuse me, over its constant, H. So its constant, you can use, since it has energy times second, you can use the version that is joules seconds, in which case you'd have to convert the energy into joules, or you can use the version that's electron volt seconds, which would be much simpler. You don't have to do any conversion. So Planck's constant in units of electron volt second is 4.1357 times 10 to the minus 15 electron volt seconds. Taking those values in, find that the frequency is equal to 4.72 times 10 to 14 hertz. If we can box our solution for part A. Part B wants us to find the wavelength, but we know that C and wavelength are related according to the above equation, where frequency is equal to speed of light c divided by lambda for things that are at the speed of light, or for photons, in other words. So frequency then, looking at that, or wavelength then, looking at that, would be equal to speed of light divided by frequency. Speed of light is in units of meters per second. So lambda is equal to c over F. Plugging in the values, we find that the wavelength is equal to 603 times 10 to the minus 9 meters, or 603 nanometers. And then lastly, part C says what part of the spectrum, the electromagnetic spectrum, is this. Look it up. You find that this falls within the visible range. So this is visible. If you want to get more specific, this is actually more like orange. It's between yellow and red, so this is going to be somewhere around the orange. That's our solution for part C.